to yes, Rafi.
For yesterday, how many pages should I read to complete the notes?
Well, I'm gonna share this with you so you can, redo them. Okay? But I don't know.
But yes, how much do you write?
How much did I write? Well, I have written it digitally, so I can't know how many pages I've written yet. Probably 5 or 6 pages, maybe. A4 sized, I
Alright.
believe. 5 or 6, perhaps. Okay. Now, today I'm gonna tell you a story of a great, great, great scientist who was not given the importance he deserved within his life. His name was De Broglie. His name is written although De Broglie, but because he's a French guy. Basically, his name is pronounced as De Broglie. Now, so he gave this idea. So let me write this. In fact, so he came up with the idea that matter and waves are interrelated. So, what he basically proposed was that all waves have a particle nature, okay, and later it was demonstrated by photoelectric effect experiment, right? So Einstein basically did that much later when he died, and he said all matter has a wave behavior. Like you, me, everybody, like anything that is a matter can be regarded as a wave, right? And at that time, when he was like there, people used to mock him. They used to say that, okay, he's a crazy guy because he basically, people believe that his ideas were absolutely bullshit. And basically, he was never ever given the right, you know, importance in his lifetime. But when he died, basically, it was picked up. And the funny thing is that he died in like something like 1980s, okay? And when people actually got to know, wow, he is actually the person who helped like Einstein to be Einstein to this day. He was awarded a Nobel Prize in 1929, like after so many years after his life. So he was appreciated finally. Do you guys understand this? So, what he gave this, when he gave this groundbreaking theory, basically, this is the basis of all quantum physics. He said that the wavelength of any mass m is given by equation lambda equals to h over p. Alright, so this is the equation that we got to learn. Lambda here is known as the de Broglie wavelength. H is the Planck constant and p is the momentum of particle. Okay, so what I want you to understand is that this equation can be further, say, expanded into something like lambda equals to h over mv, because p is momentum, so we can basically add mass of the particle that is moving, and let me write, and we can also talk about the velocity of the particle. Okay, is it clear, everyone? So basically he tried to explain this theory by, I'm gonna do it with an example, and then I'm gonna tell you why it is so important. Because when he shot an, okay, let's not be lazy, electron beam is shot at a double slit. So in AS, if you remember, right, double slit experiment was AX equals to lambda D. You guys remember this formula or no?
Yes, sir.
Okay, so an electron beam is shot at a double slit at a speed of 60% of speed of light. So they say find the wavelength of electron. Wow. So you might never, you would not have known before today that electrons have their own wavelength, right? Okay, like that. And when electron beam basically was incident on the double slit, like that, so they saw the diffraction pattern, the fringes being created because basically the electrons diffracted, like that. So these are like, this is the screen, that's the double slit, and this is the fringes. So we can find the wavelength by using, the speed, which is 60% of 3.0 times 10 raised to 8, which is about 0.6 times 3.0 times 10 raised to 8. Let's keep it this way. And then the wavelength is equal to h over mv, where h is Planck constant, which is 6.63 times 10 raised to minus 34 divided by 9.11 times 10 raised to minus 31, that is the mass of an electron, times the speed is 0.60 times 3.0 times 10 raised to 8. So the total, the wavelength would be 404 times 10 raised to minus 12 meters. Is it clear? If you notice, 10 raised to power minus 12, so I'm just going to write a note here. 10 raised to a minus 10 corresponds to wavelength of X-rays. See, like that. So electrons may have, at this speed, electrons may have very similar wavelength to X-rays, right? So it's strange that this is happening. But the idea is that to achieve this whole thing that we're talking about, we also tried grating. If you remember, basically the grating which made diffraction grating, if you remember, d sine theta equals to n lambda, something like that. So I'm talking about that. A grating with spacing of intermolecular, but let's not write intermolecular, but let's write interatomic. That's even better. Interatomic distances is arranged, and a graphite film is used. The spacing between the graphite atoms will act as slits. So we end up getting a pattern like this. Let me show that to you. So basically this is the screen. You end up getting a pattern like this, and in the exam you will have to draw this pattern. So it's like concentric circles like this, so you should draw this. And the thing is, how is it even happening? Because if you really look at an atom, it has a center, nucleus, and the next atom, and the next, like this. So because the nucleus is at the center, so between one nucleus to a nucleus, this is basically, it forms a slit opening like this. Do you understand this? Now you might have studied this, that basically the maximum observable diffraction basically happens when lambda is approximately equal to a. So they would change the speed of the electron that was directed towards the film, and then it would change, right? And the point is that when it would give the maximum diffraction, it means that the wavelength which was calculated by what de Broglie told us would be the spacing between the nucleus of that particular material which they are going through. So with this we could actually find out what would be the structure of any material that was placed in front of electrons, and that helped us go into the whole atomic structure thing. Do you guys understand what I'm saying? So behaving like a wave basically was his idea, and he said that this idea is called wave particle duality. So even humans might act like that. A tennis ball might have its own wavelength. Anything in the world that has a mass and a certain velocity will have a certain wavelength corresponding to it. Okay, how cool is that, right?
Sir, can you repeat the orange part?
Yeah. Okay. So orange part is Gatika. Did you remember like a diffraction grating? Diffraction grating was like this. There were holes, and then when the light would pass, it would create a pattern like this. You remember?
Yes, sir.
So basically, it's the same pattern it's creating, right? But this time, instead of grating, we have basically the atoms. Do you understand? So the gaps between the nucleus from one nucleus to another basically acts like an opening or a slit. Do you understand?
Yes, sir.
So what I'm saying is that we have learned in AS that when this gap A, the slit size, is equivalent to the wavelength of whatever wave is coming in, it would cause you to have the maximum observable diffraction. Do you understand this?
Okay, sir.
So when you have that condition, it means the wavelength is approximately equal to the slit opening. Now, suppose you're looking at a film, graphite film. Can you tell me by just looking at what is the distance between their nucleus and other nucleus? You can't, right?
No.
But then, if you send like electrons and they make a pattern of maximum diffraction, so you can find the wavelength of electron using this formula, de Broglie's wavelength, and that wavelength would be approximately equal to the gap between them. And now you know this subatomic structure. Do you understand the structure within? Did I make myself clear there?
Yes, sir. Got it.
Okay. Now, very, very cool. Now, so since now you understand that where we are coming from, so we are going to talk about more about Neil Bohr's experiment. And before we do that, we should understand that how do we provide energy to an atom. Okay, so let's write how to provide energy to an atom. So to provide energy to an atom, okay, there should be a question mark here. Number one, the best way is that you heat the atoms. So you provide heating, thermal energy, or basically throw high energy electromagnetic radiations. It could be UV and above, like make big difference. And the third thing is that you can provide electrical energy. And that would cause the particles to gain enough energy, and it would help them move within. So let's talk about it now. So last time when we basically wrote this whole note, we said that he observed that every vapor gas has a unique pattern, so he concluded that every material used inside the gas tube gave a spectral pattern signature to the material. So we're talking about that, right? So we are going to discuss that how that signature basically develops. So basically Bohr's atomic model looks something like this. So he has like He says the lowest state that any material can have is considered to be 1, right? So this is like the energy state. We're going to talk about it in a bit. And then we have the second one, which is 2. And there could be infinite number of them, but let's see. 3. Let's make some of them. And 4. So I'm basically purposely closing the gap, by the way, because as you go up, the difference really. So it could be infinite number of states. So we can write infinite number of possible states. The first one has a name of its own, and that's called the ground state. So you write it right now. So if an electron basically goes upwards like this, so we call this is basically going up, means that it is jumping towards high energy or excited state. So if you go up, it means the energy is getting higher of the electron. And similarly, when you jump down, it's like when you jump down like this, it's basically going to low energy state towards ground. Ground is not like a physical ground, just called ground state. And between one state to another, like this, is called a quantum gap, like that. What you see right now is basically regarded as the quantized model of an atom. This is what you see right now, like this. Hello. Walaikum salam. Walaikum salam. Yes. Okay. So, ladies and gentlemen, Is that clear to you? Any questions that you might have right now? So, basically, Neil Bohr. So, this is basically an energy structure of atom was given by him. So Neil Bohr suggested that energy, in fact, let's write, every atom has a unique quantized energy structure and has infinite number of energy levels. When an electron absorbs energy, they jump to an excited state from the ground state where basically they are, right? Okay. So an electron, this is very important, an electron in any atom will absorb a photon only if size of photon energy corresponds to energy of quantized gap. That's what you need to know. Okay. So please hold on before this point that I put a star on. You will be confused that why am I saying that they have a, basically what does this gap mean and what are the energies with them. So we're going to do that in a bit. Just for your own knowledge, I'm not saying you're not required to, remember what I'm going to write right now, but just for your own knowledge, if you ever happen to come across this, write not required by 9702 syllabus. Energy of any state is given by minus 13.6 z square over n square ev. So that's just a formula where for any atom, A is this atomic number, Z is basically the proton number. So you can basically talk about that. So to basically have a sort of a discussion, we are going to look at the hydrogen atom structure, and then we are going to talk about that, and then we're going to understand how basically these gaps in hydrogen are and what are their energies. Okay, so I'm gonna copy this, I'm gonna erase everything unnecessary. Okay. All right, so hydrogen, usually this will be given to you, so don't have to worry about it. Hydrogen ground state is at minus 13.6 ev, then the next one is 3.4 ev, then the next one is minus 1.51 ev, and then the next one is 0.85, and the next one is 0.544, and the next one is like 0.378. It basically comes from the formula above, so you don't need to remember any of this. So suppose that you got an electron heated, or you gave it a certain light, or maybe you were electrically charged, or whatever, you gave energy to it, and currently the electron has jumped to state number 4. So here it is. Is it clear, everyone? So this is basically the hydrogen quantized model. Okay. Now check this out. Remember, when we are making the changes, we will always make sure that law of conservation of energy is always followed. That is, you need to understand laws do not break in physics, so that's why. So what I want you to understand is that how can electrons move from excited state to ground state, like that. So we can say that the excited state of an electron only lasts for 8 to 10 milliseconds. After they have to move down, as they cannot retain excited state for very long. So electrons may release energy, number one, directly, so I'm gonna talk about it, or step by step. So that's something important. Okay, in 10 minutes, please, I want you to rejoin if it ends, please. So remember that. So what you need to understand is that it releases energy in form of photons whenever it comes down. Okay. Now, so for example, now we're talking about this one. It says that let's assume that an electron jumps from ground state which is n equals to 1, to n equals to 3. So let me just make it shorter, please. Okay, n equals to 3. But let's make it like 4, then I'll explain it even better, doesn't matter. N equals to 3. So by absorbing okay. Hello. You guys can hear me, right?
Yes, sir.
But somehow the screen has not changed. Let me just fix that, please, quickly. So we are like at a very, very important point right now, and we only have 8 minutes, which is sad. Okay, now you can see this. Now, so it says that absorbing energy, and then what are the possible photons released after going back to the ground state. Now, how do we really do this? So first of all, let me talk about that. So you see that if we're going to come back to the question, but I just wanted to do 4, because if it's at 4, one of the ways it can come down is by taking a jump from 4 to 3. So that could be one way it can do. And when it's doing that, it's going to release a photon of energy that is the difference between these two gaps. Do you understand this? Then what it can do is it can jump from 3 to 2, and then it will also release another photon of the energy difference between those gaps, and then it can jump from 2 to 1 in step 3, and it can release another photon of the difference of energy. That's one way of doing it, right? Then it is also possible that instead of jumping from 4 to 3, it could directly jump from 4 to 2, right? So that could be one way. So let's call this 4, and it would release a photon of difference in energy. It is also possible that when it had jumped from 1, from 4 to 3, it could have jumped from 3 to 1 like that, and might have released a photon like this. And it is also possible that it might have jumped directly from 4 to 1. So by doing this, what we're saying is that we are predicting that when it is at state number 4, it could basically give 6 type of different photons. Do you guys understand that? And it is entirely at the discretion of the electron that how he actually makes the jumps. So if it believes that, okay, I should go from 4 to 3 and then 3 to 2 and 1, you can't stop that, but you're going to receive those photons. if it decides, okay, I've jumped from 4 to 3 and now I'm going to jump directly from 3 to the ground state, again it will just release that type of photon. You can't do anything about that. And then it could also jump from 4 to 2 and then from 2 to 1, or it could decide that, okay, I'm not going to do it in step by steps, I'm going to jump directly from 4 to 1 and I'm going to basically release the biggest photon that I can. Is it clear, everyone? All right. Now, so in the question it says that now it's basically going from, if it was at ground state, like it was here till 3. So let's just, to make it quick enough, I'm going to copy this part only so that we can, do it here. Okay, so I'm going to erase everything that's not required, and then we're going to find what is the size of photon just now. So in this question it says the electron is at 3 and now it needs to make jumps, right? So one way the electron can come down is by going to 2 first, releasing a photon, and then from 2 it can make a jump to 1 and release a photon, or it could directly jump from 3 to 1 and release a photon. So how many possibilities are there that how many different possible photons can it give? Can somebody please tell me? Yes. There are only 3 possibilities. So now let's find what would be the size of that photon. So I'm going to do the first one and then I'm going to give you the homework for the rest of them. Okay, so let's try the difference of energy when it makes a jump from 3 to 1. I just want to show you this, how I'm doing this. So because energy is a scalar quantity, so you're going to basically find the change in energy by putting the largest possible energy first minus the smallest. So in basically scalar quantities we do that. So this change basically gives me 12.09 electron volts. You can check from the calculator as well. Okay, so now I will change it into joules. So to change it into joules, 12.09 should be multiplied by 1.6 times 10 raised to minus 19 joules, because 1 EV is this. So I'm going to get 1.93 times 10 raised to power minus 18 joules. So this is the amount of energy that this photon will have. Okay, then because I know photon energy is equivalent to hc over lambda, so what I'm going to do is I want to find the lambda. It is 6.63 times 10 raised to power minus 34. The speed of light is 3.0 times 10 raised to power 8 divided by the energy of the photon that was released when it made a jump from 3 to 1 is this much, and then I'm going to get it as 103 nanometer. You can check it too. The interesting thing is that this is the wavelength of UV light. So basically, when an electron in a hydrogen atom jumps from 3 to 1, it is going to release a photon of this wavelength, which corresponds to UV light, so we can detect it. Do you guys understand this? Alright. Gatika Aman.
So we don't include the values between 1 and 2?
We will do. So now what you're going to do today, your homework is for the next week, is that you're going to find energy from 3 to 2 and then you're going to find the wavelength, okay? And then for then you guys are going to do energy from 2 to 1. So you're going to find the wavelengths of all the photons that are released. Is it clear? So I've done one of those for you.
But still, when we do 3 to 1, we should add that, right?
When we have
When we are doing the calculation from 3 to 1, shouldn't we add that value also?
which value? No. Why?
The one between 2 and 1.
2 and 1. No, why? I've just subtracted the energy of that state from the energy of the receiving state. Do you understand? So to find the difference in energy between two states, you just need to subtract the energy at 3 minus energy at 1. Do you understand? So suppose I'm doing 3 to 1, 3 to 2, then I'm going to subtract minus 1.51 from 3.4 then. Do you understand? Like that.
Yes, sir.
So will you be able to do this? Yes.